Let's continue on with section 11.2 in chapter 11 on drag and lift. And here we're going to be looking at the flow over a circular cylinder as a way of looking at the drag coefficient. And we're going to talk about how the drag coefficient is related to the drag force for not only cylinders but other objects. And we will look at how we can use the coefficient of drag and determine it and find values of it. And then also in sections 2.2 and 11.2 and 11.3, we'll figure out how to calculate the drag force through examples that we'll do. So let's continue on then. And the definition of the drag force, in addition to being able to be defined as we saw it before in terms of form drag, which is due to pressure distribution, the pressure distribution on an object, and the friction drag, which is due to the shear stresses. In addition, we can write the equation this way, or we can write it in terms of the non-dimensional number, which is called the coefficient of drag. This is a pi group, and A is some reference area of a body that that's under consideration. It might be an airfoil or a cylinder or a sphere inside the fluid. And then of course we have this term here, which looks like the kinetic energy to some extent. It's got the density of the fluid and the free stream velocity. So this is basically kind of an energy density term. So the idea then is to, one way of looking at drag in fluid dynamics or fluid mechanics is to express the drag coefficient. So it's defined as being the drag force over the reference area times the kinetic pressure, or the kinetic the energy density, if you will. And it's usually determined by experiment. Again, these are it's very difficult to predict using equations how the flow is going to be around an object, and so a lot of times we'll do experiments to determine the drag force, the coefficient of drag, and the drag force. And so here are some examples of how some experimental data, basically, from different objects. And so we have a number of things. We have a circular cylinder around which we can see at low Reynolds numbers. These are very small Reynolds numbers, less than 0.1. We can see that the drag decreases very quickly until it gets up to about 1,000. And through this regime, we have a very, at least for cylinders, we have a very constant change of the drag force with over 2 orders of magnitude, from 1,000 to about 10,000. The value is quite constant. It's almost 1. And then when we reach a Reynolds number of about 10 to the 5, we have a very large decrease in this drag, and we'll see, or in this in the coefficient of drag. In a minute, we'll see why that's so. But first of all, let me also say that for what's called a streamlined strut, kind of looks like an airfoil here, this shape, we have a similar curve, although it's kind of shifted towards higher Reynolds numbers. So a rapid decrease in the Reynolds number to about 10 to the 5, and then for this object, it gets pretty flat from 10 to the 5 to 10 to the 7. The interesting thing is that the drag coefficient for a flat plate and a square rod are actually quite independent of the Reynolds number. We can see that they're absolutely flat between 10 to the 4th and 10 to the 6th here for this experimental data. And this is because these bodies, they cause flow separation, and therefore it turns out that the drag force is purely due to the pressure distribution and not shear stresses. And so it turns out that only the friction drag is a function of the Reynolds number, and the form drag is not. And since the drag of these two objects is purely due to the pressure distribution, or the form drag, they do not, the drag does not depend, at least over this interval right here, over these Reynolds numbers, does not depend on Reynolds number. So another couple other things I wanted to say are some definitions. These are called two-dimensional sections, and they're kind of idealizations. They're assumed to be kind of a uniform section area with where the flow is independent of the ends of the objects. And so normally we're looking at very, very long objects, like in some cases we might even idealize them as being infinitely long. And one rule of thumb to use these data is to realize that the length of the object to its diameter, or to its relevant length, it might be b, little b, as you can see here. Here's d. Let me make that a little d. So the length over the relevant dimension, it's either d or b here, is going to have to be greater than or equal to 20. So in order to use these data, so basically the length to the width, if you will, or the cross section of these objects has to be quite large. The length has to be very long. So when we have something like a cylinder where we have LD being comparable to 1, this is going to give us edge effects, or what I would call end effects. So the drag is going to be affected by the flow around the ends. But when we have this situation with L over the dimension being greater than or equal to 20, we don't have to worry about that. The object is, for all intents and purposes, infinitely long. Another thing is in addition to calling these two-dimensional sections, aerodynamicists, people who work in the aerodynamics industry, call these sectional drag coefficients. So this is an alternative sectional drag coefficients. So you might see this term used in some of the literature. And these are used actually to estimate the sectional drag coefficients that the aerodynamicists determine are used to find the drag coefficient. So, so we have some data on how to, as a function of Reynolds number, we have some experimental data shown here to determine the drag coefficient, which will allow us, through this equation here, or this equation, to be able to determine the drag force. So it's a big step forward if we can find that drag coefficient. So it turns out that we saw before that that these three regimes for this circular cylinder. So this section kind of focuses in on that, and we see that for Reynolds numbers of less than about 1,000, the drag coefficient is going to depend on both form and friction drag. And since it depends on friction drag, we see a very large dependence here. The friction drag is quite large for low flow, or for low Reynolds numbers. And then we reach a regime here where, as I mentioned before, that this is fairly constant. And this is because it's caused by form drag pressure distribution, which is fairly constant through this area. And then after, for this regime, actually that should be a greater than sign. Just notice that that's incorrect. For the Reynolds number being greater than 10 to the 5, the boundary layer becomes quite turbulent, and we see a rapid drop off, at least initially, in the drag force, and then a kind of a return. So it becomes much more variable out here beyond about 10 to the 5. And so this is because, just to give you kind of a physical idea of why this occurs for a circular cylinder, it's because when the flow around the cylinder has a Reynolds number between 1,000 and 100,000 here, we note that the the pressure looks like this, and we see flow separation occurring kind of back behind or maybe on the side here of the cylinder. But when we go to high Reynolds number, this separation area pulls around to the back. This low pressure zone is much smaller and is confined to a smaller region in the back of the cylinder. And this occurs, this graph is for about 5 times 10 to the 5, about 500,000. And so this area of flow separation away from the object influences the drag, as we might expect. So turns out, not surprisingly, that surface roughness impacts the drag force as well, or the drag coefficient, and so and therefore the drag force. So we have again the drag coefficient. This is now a linear scale for different cylinders with different roughnesses, and so they're defining kind of a new parameter here, this KD, K over D. This isn't the sand roughness anymore, but it's like it. So it's some roughness of the cylinder over the diameter of the cylinder. And these are plotted against the Reynolds numbers here. Again, note that the Reynolds number is being calculated as the free stream velocity times little d, which is the diameter of the cylinder now, and divided by the kinematic viscosity. So little d is the relevant dimension here for the Reynolds number. But we've got a series of curves here, starting with the smoothest. You can see that this is what the Reynolds or the drag coefficient looks like for a smooth cylinder. And as we get rougher and rougher, the drag actually kind of increases at a comparable. It kind of increases as you go back in this direction. And as we get to the roughest cylinder with a K over D value of 6.3 times 10 to the minus 2, we can see that once it becomes rough enough, the boundary layer becomes turbulent even at low Reynolds numbers, and so we have a constant drag coefficient for as a function of Reynolds number. Note that these Reynolds numbers are quite large. They're starting at about 4 times 10 to the 4, so this is getting close to the turbulent regime, as you can see. And so again, these, if we know the roughness of our cylinder, we're able to read this off this chart and use this to determine the coefficient of drag at a particular velocity or Reynolds number for a particular sized cylinder. So that's it. The basic idea here in this section was to introduce the idea of the coefficient of drag and how we can find this for two-dimensional sections. And again, this was an idealization of kind of an idealization of an infinite cylinder, or an infinitely long or nearly infinitely long section, like a cylinder or a flat plate. And by infinite, we mean that the length of the area or the body over its relevant cross section needs to be greater than or equal to 20. So once we have these coefficients of drag, we can move forward to determining the drag force. And the next section, you can see, is talking about drag on three-dimensional bodies, where we no longer assume that they don't have end effects. We're going to deal with the end effects. So we'll deal with that next. Thanks.